the last section of our electrolysis option involves using electricity to extract metals. Now, there are 4 metals we have to look at. First is lead, the second is sodium, then there's aluminium, and then there's iron. And the chemistry behind the extraction of those metals is something that you do have to know in considerable detail in order to answer the questions in the option, should you decide to do so. So we're just going to go through this as quick as we possibly can. There's an awful lot of animations on this thing that I've attached to each slide, so I'm not going to really dwell on each of them per se. I'll go through the chemistry quickly, but I would ask you to view the animations, view the little links that are at the bottom of the slides, and make sure, sometimes you might have to go into a site and click twice or 3 times to get forward to the animation itself, but just make sure that the animation clarifies any questions you may have on the extraction of any one of the 4 particular metals. So the first one we're going to look at is the electrolysis of molten lead bromide. Now, the first thing I want to draw your attention to is this word here, molten. And that simply means that the only thing that is present inside in this cell is Pb2+ and Br-. Okay, so when they dissociate, as they will, as soon as you melt them and they dissociate, they'll form 1 lead ion and 2 bromide ions. Okay, and then the rest is history, because now we understand that if we have a battery, and remember our electrons are going this way, so that means this is going to be negatively charged. All the electrons will be down here waiting at the end of this to be picked up. So the positive lead ions, they are cations. They will approach the cathode, they will take up their 2 electrons and become lead metal. And when they do that, they will simply adhere to the outside of this particular cathode, and the cathode will build in mass. Okay, so lead ions, which are present in the molten lead bromide, they'll make their way over to the cathode, pick up their electrons, and then Pb2+ picks up 2 electrons and becomes lead metal and deposits itself on the surface of the cathode. At the anode, which is where the electrons are deposited, the bromide ions, which are each carrying an extra electron, they will be attracted to the anode, so if they're anions, they will surrender their electrons, and when one bromine surrenders 1 electron, it just becomes Br. But bromine, being a halogen, must exist as a diatomic molecule, so therefore we need 2 of those to surrender 2 electrons to become Br2, just the way I have the equation that is down there. So a very, very simple thing to do. The only thing I want you to watch for is the word molten, because if it's molten, well then there's only lead and bromine in there, or in this case lead and bromide ions. Okay, the second metal is sodium, and sodium is extracted industrially by this large apparatus that we call a Downs cell. And the Downs cell, that's its actual name, the Downs cell involves a graphite anode. Now, graphite is simply carbon. It's the stuff that runs through the middle of your pencil, okay? The graphite anode, and then a circular, I don't know if you can see it here, a circular steel cathode. So it runs around this like a collar around the graphite anode. And again, what's present in here is molten sodium chloride. But there's a problem. In order to melt NaCl, we need temperatures that are in excess of 900 degrees Celsius. So NaCl will not melt until you go over temperatures of about 900 degrees Celsius. Now that's extremely inefficient for industry because it's energy intensive. So what they do is they mix in some calcium chloride, which they call cryolite. And this calcium chloride, when it is mixed with sodium chloride, gives a mixture that brings the melting point way down, roughly to about 500 degrees, and makes it far more energy efficient to use as a molten liquid. Okay, so just keep in mind NaCl by itself has a very, very high melting point. For industry, impracticably high. So they mix it with CaCl2. This mix will reduce the melting point to something that is industrially more favorable, and then the chemistry begins. So when you melt the NaCl and the CaCl2, what's present? Well, there's NaCl, Na+, and Cl-, and there's Ca2+, and there's Cl-. Okay, so obviously we're going to get the sodium being the plus, being the cation, the Na+, moving towards the cathode. So the sodium will move towards this cathode here, which is negatively charged, and when it gets there, it will pick up 1 electron and become sodium metal. Okay, now where does the sodium metal go? Well, sodium metal is less dense than molten sodium chloride. So all of a sudden it floats. You can see it there in that layer just up here. Yeah, it floats and it is tapped off upwards. So it leaves this way and it's tapped off through that tube there. Okay, so that's the chemistry that happens with the sodium. At the graphite anode, we have chlorine with its extra electron surrendering that electron and becoming Cl. However, chlorine again is a halogen, it's a diatomic molecule, so you need two of those to surrender 2 electrons to give Cl2. But if we surrender 2 electrons, well then here we must give in 2 electrons, okay? So at the cathode we must take up 2 electrons here, so 2 of them will take up 2 electrons to become 2 sodium. So just make sure you've got your electrons balanced as we move along. So there's three things to remember here with the down cell. First of all, sodium chloride has a very high melting point, too high to do industrially. We mix it with CaCl2. It brings down the melting point to an industrially favorable temperature. And then when it's melted, the graphite anode will look after the chlorine by taking in the electrons from chlorine and forming Cl2. And then the circular steel cathode will then give the electrons to the Na+ in order to form the sodium metal. The sodium metal then floats on top of the molten sodium chloride and it's tapped off upwards. Just one interesting side. The chlorine gas is not what we want here. We want to extract sodium. But one of the byproducts obviously is going to be chlorine gas. But because it's chlorine gas can be sold to the medicinal agencies in order to make bleaches and disinfectants and anything at all that's got to do with killing bacteria. Okay, so the Cl gas, although it's a byproduct, will be bottled and sold so that at least some money comes back to the factory to maintain this process. Okay, so there's what we talked about already. The calcium chloride is added to the molten NaCl to reduce its melting point. The chlorine produced is collected as a useful byproduct. And at the anode, we have chlorine surrendering electrons to become Cl2. At the cathode, we've got sodium taking on electrons to become sodium metal. And the sodium metal is what we want. The chlorine, being a byproduct, is bottled and sold. Okay. Then we move on to the third metal. And the third metal is the extraction of aluminium. Now, aluminium is taken from the earth as an ore, as a compounded ore. And the compound that aluminium is found in is a compound that is called bauxite. Okay? And bauxite is found in pockets maybe around parts of Africa and so on, but it's found in the ground. It has to be mined. It has to be dug up from the soil and brought in order to be, first of all, purified before the aluminium can be extracted by electrolysis. So with the extraction of aluminium metal, it's a two-stage process. First of all, we have to purify the aluminium, or the bauxite, the ore, to extract the aluminium oxide. And then we've got to electrolyze the aluminium oxide in order to give us just pure aluminium. Okay, so it's a two-stage process. Don't forget that. First of all, as we said, the aluminium oxide must be extracted from the ore from the earth, which is bauxite. And then secondly, the aluminium oxide, when it's purified, will undergo electrolysis. First stage, how do I get the bauxite, which is the earthly ore? How do I get the bauxite down into pure aluminium oxide? And the answer is by a stage 1, which has many different procedures. The first one is what we call digestion. Now, look, we already know as chemists that the smaller the particles available for reaction, the faster the reaction. So if you're digging this from the earth, you're going to get fairly decent clumps of soil, okay? If you left them like that, they wouldn't react very, very quickly. So here what we do is we simply crush it. And when you crush it, you increase the surface area and you increase the speed of reaction. When you crush it, you add it to hot sodium hydroxide. And that mixture then is pumped into what we call digesters. Now, a digester is basically somewhere where you allow a chemical reaction to take place. And in this digester, under high temperatures and pressures, this is where the reaction will take place with the NaOH. Okay, so crush the bauxite, add it to hot NaOH, and put it into digesters to allow the chemical reaction to proceed. Aluminium oxide will contain this here, what we call water of crystallization. So this is in your bauxite. in a highly impure form, okay? And what we want to do is we want to get this impure form into a pure form. So the first thing we do is we crush it, we add it to the hot sodium hydroxide, we put it into a digester, and the reaction that takes place there will form what's called sodium aluminate. And there's sodium aluminate here, and 4 molecules of water. So in other words, we're driving off the water of crystallization to leave behind sodium aluminate. Now, the sodium aluminate has to then be turned into aluminium oxide. And the way in which we do that is at this stage to get rid of the impurities, okay? So once we have the sodium aluminate ready to go, we add in flour as a flocculating agent. Now we had that in the water treatment process. You add in flour, and what it does is it causes the particles of the impurities to flock together and fall to the bottom. And when they fall to the bottom, what you get at the bottom is a sludge that is red in colour, and that's called red mud. Okay, and that's tapped off from the bottom, so that what is left at the end of this clarification stage is relatively pure aluminium oxide. At this stage, once you have your aluminium oxide ready to go, you take tiny pure crystals of the substance that you want to grow, which is obviously aluminium oxide. So you take little crystals of aluminium oxide and you seed the sodium aluminate with aluminium oxide. And what these little seeds do is they actually promote the extraction of aluminium oxide. So when you put these little seeds of pure aluminium oxide into the sodium aluminate, they trigger the reaction that brings out the aluminium oxide in large numbers. Okay, so tiny little crystals of aluminium oxide are used to help in the formation of larger crystals. And this is the way in which it happens. The sodium aluminate will turn into the aluminium oxide that we require and the sodium hydroxide, which basically we take away. So at this stage, we have relatively pure aluminium oxide. Now, you might say to yourself, well, isn't that what we started with? Yes, but we started with bauxite, which had an amount of aluminium oxide that was impure. We've gone through the digesting process with the hot aluminium oxide. We've gone through the formation of the clarification, where we put in the powder and allow the red mud to settle to the bottom, take it away. And at that stage then, we seed the sodium aluminate with crystals of aluminium oxide, which is pure. And that triggers the formation of pure aluminium oxide, which now we're going to stick into the electrolysis cell and we're going to electrolyze it to get the pure aluminium. So the first stage is like, it's a purification of bauxite, which contains impure aluminium oxide, and we want to get at the end of that pure aluminium oxide, and now we have it. So to finish, as we said already, the aluminium oxide then is heated, and the reason why it's heated is to drive off the water. So at the end of that, we get exactly what we wanted. We get the white, pure aluminium oxide powder. Now stage 2 is where the electrochemistry comes in, okay? Because stage 2 involves taking the aluminium oxide and melting it. But again, we've got the same problem we had when we were trying to do the previous one with sodium chloride. The melting point of aluminium oxide, pure aluminium oxide, is very, very high. So in this case, we add in cryolite, okay? And the only reason why we add in cryolite is to bring down the melting point of the Al2O3 to an industrial preferred temperature. So instead of having an energy inefficient system where we have to put in high amounts of energy to melt this thing, we mix the aluminium oxide with cryolite. It gives me a mixture that has a lower melting point and is industrially favorable, very similar to the electrolysis or to the molten NaCl. Okay, so when we do that then and we melt it, we then put it into the electrolysis cell itself. And what we notice is in this situation here, both the anode and the cathode are both made of graphite. Okay, now graphite, as we already know, is an active electrode. Graphite, because it's carbon, can allow chemical reactions to happen with it, not just on it, but with it. So what we'll notice here over time is this, that the anodes, the ones that are positively charged, they will react with the oxygen that comes from the aluminium oxide and form carbon dioxide. So over time, we'll notice that the anodes will wear away as they're being turned into carbon dioxide, and that carbon dioxide then as a gas enters the atmosphere. So this is an example of where we see active electrodes in progress. Okay, and as well as that, if we take away the oxygen, if the oxygen bonds with the carbon in an oxidation reaction, the oxygen then is taken away from the system completely, and that should leave then at the cathode the ability to form pure aluminium. So it looks something like this. At the anode, we've got 2 oxygen ions picking up 4 electrons to give oxygen gas. And that oxygen gas reacts with the carbon. Just as a reminder, the carbon, which is in the anode, then reacts with the oxygen and becomes CO2, which traps the oxygen and takes it out of the system altogether. So we don't get the aluminium oxide reforming. We get pure aluminium left behind. And then at the cathode, we have the aluminium 3+, picking up 3 electrons in order to give pure aluminium metal, which is then collected downwards. It falls to the bottom and it's collected downwards as a molten metal. Okay, so overall what happens? The aluminium oxide is turned into aluminium metal and oxygen gas, and then we can balance that. As you can see, you could say to yourself, multiply everything by 2, so it could be 2 of these and 4 of those with 3 of these. Okay, but mathematically speaking, that's perfectly fine. Chemically speaking, it will be the one with the red coordinate, the red coefficients. So the production of aluminium is a very energy expensive reaction. So that's why at the very beginning we mix it with cryolite to bring the temperature down, so that at least in the beginning it's not too energy intensive. But as it goes on, and as the electrolysis is involved, we notice that the energy needed to get this aluminium out is quite expensive. We used to have one actually down in the south of Ireland somewhere. There used to be an aluminium extraction plant, but it actually proved too expensive to run, so it closed. And it closed, it's gone about 15 years now at this stage, but it closed with, again, a loss of a certain number of jobs. But this is what the cell looks like. So you put in your aluminium oxide, okay, you mix it with cryolite, the melting point is brought down, it's zapped to melt it, and then we add in these graphite anodes. And around here, on the inside of this container, is a graphite cathode. So if you have aluminium oxide, what will happen is you'll get Al3+, and you'll get O2-. Okay. Now, what will happen if we take both of these at each of the respective electrodes? The aluminium is attracted to the cathode here. So the aluminium, the Al3+, will pick up 3 electrons, that's over here, yeah, and become aluminium metal. The O2-, which is the other part of this molecule, the other ion, the oxide ion, that will come over here to the anodes. All right, and what will happen is the O2- will surrender 2 electrons to become O. Now, you and I know that oxygen is not a monatomic element. Oxygen is a diatomic element. So therefore, 2 of those will surrender 4 electrons to become oxygen gas. But the oxygen gas doesn't just bubble away. The oxygen gas then adds to the carbon in the anodes, forms carbon dioxide, and then bubbles away. So that over time, you'll notice that these will just wear away. And they'll wear away to such a degree that they have to be replaced quite frequently. So there's money involved in keeping these anodes refreshed and making sure that the anodes can do the job that they need to do. So there's an example of where the active electrodes are involved in electrolysis. So just to summarize, what did we do? We took the bauxite from the ground, we crush it. That means we want to increase the rate of the chemical reaction. We add the bauxite, which is impure aluminium oxide, to sodium hydroxide and put it into digesters. At this stage, a chemical reaction takes place that forms sodium aluminate. Yeah, sodium aluminate. And that sodium aluminate then is brought and further purified by what we call clarification. Flour is added in, flocculation takes place of all the impurities, pulls them to the bottom, and then removes any bits and pieces that we don't want. Okay. At that stage, we've got pure aluminium oxide. So we seed it, and we seed it with tiny crystals of pure aluminium oxide, which will then enhance the growth of pure aluminium oxide. The aluminium oxide then is taken, crushed again, mixed with cryolite. So that means we're going to mix it with a substance to bring down its melting point, thrown into this large electric cell, and then zapped with a carbon cathode around here and carbon anodes up here. The carbon anodes move and they come down and they put themselves into the molten aluminium oxide. At that stage, the aluminium goes to the cathode and forms aluminium metal. The oxygen goes to the anodes and forms oxygen gas, which then attacks the carbon, forms carbon dioxide, and leaves. Okay. One of the processes that we can do then to the aluminium once it's formed is, if we go back to when we were talking about corrosion, aluminium is one of these metals that when it corrodes and builds up a layer of its own oxide, keeps the oxide layer on, forms a barrier between the metal and the atmospheric elements, and then actually prevents further corrosion. So if we were able to do that to the aluminium that we have just taken out of this electrochemical system, then we could actually sell aluminium that has a layer of aluminium oxide already built in. And the lovely extra thing about aluminium oxide's layer is that it's porous, okay? So if I was to dip it into any chemical dye, I can get green aluminium, I can get yellow aluminium, I can get red. Hence the reason why people have aluminium front doors of all different colours. They build up a layer of aluminium oxide, then they dip it into a dye. The dye can get into the aluminium oxide and it can coat it with a colour, and it can actually change the colour of the aluminium oxide to make it, I suppose, more eye-catching for people who want to buy these things as windows and as doors, or the body of an airplane, or indeed the body of a phone, or the body of a watch, you know, rose gold and all that kind of thing. Yep, that's anodized aluminium. But what does it mean by anodizing aluminium? It simply means that you take a piece of aluminium, you put it into a simple cell as the anode, and you place it into sulfuric acid. Okay, you switch on the cell. The other particular cathode can be anything. It can be graphite or lead or aluminium itself. Doesn't make any difference what the cathode is made of, but the anode has to be aluminium. And what happens is that once the aluminium becomes an anode and positively charged, the OH minus ions from water will be attracted to the anode, where oxygen will be formed, which will then attack the aluminium, form a layer of aluminium oxide, and hence stick to the aluminium and give us a protective layer against further corrosion. So it is an industrial process that speeds up a natural process that would happen under normal conditions if the aluminium was exposed to the elements. Okay, so therefore something like this. So you have your power supply here. The electrons are going this way. Okay, so that means that this one here is going to be the cathode. This one here is going to be the anode, and this is the aluminium object that I want to build up a layer of protection on, this little head here. Okay, so in the electrolyte we have sulfuric acid, and the only reason why we have sulfuric acid is to make sure that we've got plenty of H plus and OH minus ions. So when this thing happens, when this thing is switched on as it is now, the cathode, being negatively charged, will attract the hydrogen. So H plus will pick up an electron and become H, but it's H2, so it's two of them and two of them. Okay, the OH minus will come over here to the anode and it will surrender an electron and it will become H2O and O2, okay, or a half of O2. So two of them, and then we need two of them and two of those. Okay, so that's what will happen here. So we'll have the water and the oxygen. Now, the oxygen that's formed will attack the aluminium and form aluminium oxide. And that aluminium oxide then will stick to the surface of this object, this little face that's here, build up a protective layer of its own corroded material, stick to it, and prevent further corrosion. Then, once you have that layer of aluminium oxide, you can dip it into various different synthetic dyes and you can change the colour to suit the market. Simple as that. Okay, so the new oxide layer, it is porous and it can be dyed like window frames, saucepan lids and so on, and you get something like that. Okay, so you get different coloured aluminiums, and that reaction that's there at the anode and the cathode, that's what I went through a few minutes ago. So don't worry about that. That's the chemical reaction from the anodization. The last one is the manufacture of iron and steel. Now again, this is a very chemical intensive process because a lot of chemistry to remember in this one. But again, the process is quite easy. What we're doing is we're taking iron from the ground. Now iron exists in the ground in two states, as hematite and magnetite. Okay, so hematite, H-E-A-M-O-T-I-T-E, so hematite, and you also have magnetite. Most interesting names because of the fact that hemoglobin, iron. So anything with hemo is iron, and magnetic. So you have magnetite, which is nothing more than naturally magnetic iron, and you've got hematite, which is an ore coming from the ground that contains a certain amount of iron. Okay, so it is easier to extract iron from either hematite or magnetite, since it is lower on the activity series. Okay, so if we take the activity series, poor spelling can mean absolute zero in. So it's down there, just before lead and just, yeah, very low. So it's quite easy to pull out. It's not a very reactive metal, so we can get this thing out quite easily. The ones higher up, the aluminium and the sodium, they're quite difficult to extract because they're quite high on the activity series. So a lot of energy has to go in to pull these out here. With iron, we don't need a lot of energy, but we do need a lot of chemistry to get this thing out. Okay, so I'm going to bring you through the chemical process of the extraction of iron. It's extracted by a chemical reaction, we know that, and the reaction that we're going to use here is chemical reduction. Now, what's reduction? Reduction is either the removal of oxygen, the addition of hydrogen, or the addition of electrons. Okay, in this case, the reduction that we're talking about here is the removal of oxygen. Just keep that in mind. So we want to remove the oxygen from the hematite and the magnetite that is present. And one of the best things we have, one of the best elements we have as a reducing agent, an element that's almost an oxygen sponge, is carbon. We had it with the aluminium. The oxygen attacks the anode, forms carbon dioxide and disappears. Okay, so carbon is a real oxygen sponge. It's a very, very strong reducing agent. And reducing agent means it has the ability to pull oxygen off other substances. So this is the big, huge apparatus that people use in order to get iron to be reduced from one of its ores. And basically what we do is we throw the ore directly into this blast furnace. And it's called a blast furnace because air is blown up through this thing from the bottom to the top. And at this stage, I think we do realize that when you blow oxygen onto something that's hot, it increases the temperature. So we're blowing air in here to get the center, the core of this thing at a very, very high temperature. All right. And the lovely thing about this thing is that once we get it there, it will maintain its own temperature because all the chemical reactions that are about to occur now will be exothermic. So that means once you get it to the temperature at which the reactions will occur, they will maintain their temperature themselves through the exothermic reactions that take place. Now look what's loaded in the top. There is iron ore, which is your hematite or your magnetite, limestone and coke. Now you might ask yourself, why does iron have to be loaded with limestone and with coke? For two reasons. The limestone, its only job is to pick up the impurities, bond with it and fall to the bottom. Okay, so that's the only job of limestone, is to pull out all the impurities, stick the impurities to itself and fall to the bottom. Coke, which is nothing more than pure carbon, has only one job, and that's to reduce the iron oxide to iron. So there are two small chemical processes taking place here. Now, how does that occur? How does the chemistry occur? Well, let's take a look. First of all, these three elements are charged in from the top. So there's your ore of iron, that's your hematite or your magnetite. That's your coke pellets, which you'd buy for a barbecue. Same thing. The barbecue charcoals. This is exactly the same thing here. And then your limestone. Okay. And your limestone is for the impurities. They just look after the impurities. All the carbon, the calcium carbonates there, they look after the impurities. They take all the impurities out. Whereas the coke is going to do the reducing. The coke is going to take off this oxygen here and give you the elemental molten iron. Now, how does it do that? Well, by the following chemistry. Hot air is blown into the bottom to initiate the following endothermic reaction. Iron oxide with the coke itself. What happens? Well, the coke is a reducing agent. The coke will rip the oxygen from the iron. Yeah, it will rip this oxygen here. So that coke basically takes that oxygen, forms carbon monoxide, and leaves elemental iron behind. Now you might be surprised that it doesn't produce carbon dioxide. The reason for that is because the carbon monoxide is even a more powerful reducing agent. carbon monoxide is almost like the halfway stage between carbon and carbon dioxide. And the carbon really wants to go and get carbon dioxide. So the carbon monoxide is a very powerful reducing agent. And it wants to go back and get more carbon in order to finish off the job as carbon dioxide. Okay, so functions of the coke itself are, first of all, it acts as a reducing agent in that it's going to take the iron oxide and remove the oxygen from the iron to give you iron metal and carbon monoxide. That's the first thing. The second thing then is it's our fuel. It's like putting coal into a fire. It is going to burn and give us the exothermic temperature that we need at the center of this furnace. And once it begins to burn, it's exothermic and it maintains its temperature. Okay, so the first reason we want it, it's an excellent reducing agent. Pulls the oxygen off the iron oxide, gives you iron. The second reason why we need it is because it's the fuel. It's the fuel that's going to keep this thing burning. And lastly, I don't know whether you've ever had these in your hand, the charcoal pellets for a barbecue. They're light, but they're extremely porous, which means that you can load them into the blast furnace. Gases can move up through these little blocks of charcoal and molten metal can trickle down through it. Okay, so because it's porous, as we said already, it allows the hot gases to rise through it and the molten iron to fall down through it. So it doesn't block up the system. It allows things to move around the blast furnace and reach the positions where they should be. Now again, there's a lovely link down here that I want you to look at, which will bring you through that process in greater detail. Okay, what's the function of the carbon monoxide? Well, as I told you already, carbon monoxide is a reducing agent again. It's the halfway stage between carbon, elemental carbon, and carbon dioxide. So it's like the unfinished carbon dioxide, and it has to get finished. So carbon monoxide will go in search of any other oxygen that's there, take it, finish the transition to carbon dioxide, and then disappear into the atmosphere. Okay, it is the main reducing agent. It's the one that gets really oxygen hungry. Now you might say, well, carbon is oxygen hungry. Yes, but carbon monoxide is only one step away from carbon dioxide. So it becomes more hungry for oxygen, and that's why it's the main reducing agent. What it does is it then goes back, finds more of the iron ore, the hematite or the magnetite, again takes the oxygen here to itself, finishes the transition into carbon dioxide, and gives you your molten iron. Okay, so what does carbon do? Carbon acts as the initial reducing agent, finds iron ore, takes off some of the oxygen, gives you iron, but in that process forms carbon monoxide. Then the carbon monoxide, which is really hungry for oxygen, finds more iron oxide in bauxite or hematite, rips that carbon off to give you more molten iron, but this time finishes the transition of carbon monoxide to carbon dioxide. Residual carbon monoxide, as we said already, is burnt with other waste gases to maintain the heat of the furnace. So all of these reactions that are going on inside, they're exothermic. So once you get that stove or that furnace up to its operating temperature, it will stay. As long as you keep loading in the sun from the top, that temperature will maintain itself. The limestone, as we said already, has one job, and that is to remove the impurities, mainly of silicon dioxide. Now, silicon dioxide is better known as sand. So if you're taking iron oxide out of the earth and you're throwing it into the top of this blast furnace, a whole heap of sand is going to go in as well. The calcium carbonate finds the sand, which is silicon dioxide, bonds with it, and forms a new compound called calcium silicate. Okay, and calcium silicate, which is this one here, CaSiO3, that's calcium silicate, that later on becomes a grey powder, and that grey powder is bagged and sold to the building industry as cement. So there's no waste here. Even the impurities themselves, after they have reacted with the calcium carbonate, are giving us cement, which can be bagged, dried, bagged, and sold to the building industry. Okay, so even the impurities are worth money at the end of this. How does it work? Well, the calcium carbonate, remember, is limestone. Limestone will decompose into two things, calcium oxide and carbon dioxide, and then the calcium oxide goes looking for the impurities, which is the silicon dioxide, bonds with it, and gives you the CaSiO3, which is not a calculator. It's not Casio. It's calcium silicate. Okay. The slag, that's what it's called, is tapped off at intervals and used for road building and cement making. So again, there's money involved even in the impurities itself. Molten iron is then tapped off into pigs. Now, pigs, it's a great chapter actually, slags and pigs in the one slide. Okay, where would you get it? So the pigs are like little kind of trolleys, and they roll up, the iron is tipped in, and they take it away. Okay, I don't know whether you've ever heard the phrase before about pig iron. Yeah, if somebody said, but he did that just for pure pig iron, it means stubborn, brittle. Pig iron is very, very brittle iron. Okay, it has to be further treated and refined in order to get it to the standard that is needed for building and for what iron would normally be used for, the body of a car and so on. But you certainly wouldn't sell it as pig iron. If you do sell pig iron is used in relation to, let me think where you get it. You know the big manholes in the middle of the ground, yeah? They're very, very thick, they're extremely heavy. Also, the big shores that you have that allow water to flow down when there's rain, they're made of pig iron. But it certainly is not industrial iron. It's almost iron that is just used to give something bulk and weight, but it has no strength whatsoever. It breaks very, very easily. And if you were to hit it hard, it can actually shatter. Okay, so pig iron is not good iron. Pig iron needs to be further treated. So, what happened? We took our hematite, or our magnetite. We threw it in the top together with limestone and coke. The iron ore, first of all, met the carbon monoxide. Sorry, met the carbon. The carbon took the oxygen to form carbon monoxide. The carbon monoxide then attacked the ore again, removed the oxygen from the iron oxide and gave you molten iron, and that's good. And it finished the transition then to carbon dioxide. As we said, the iron itself, iron oxide, some of the carbon takes some of the oxygen, but it's the carbon monoxide that really goes oxygen mad. It goes looking for oxygen, it's really hungry for oxygen, and that is what mainly produces most of the iron in this blast furnace. What does the limestone do? The limestone decomposes into calcium oxide and carbon dioxide, and the calcium oxide reacts with the silicon dioxide, which is sand, forming calcium silicate, which is nothing more than slag, which is used in building roads and used in cement making. Okay, and again, there's a link down here. Have a look, go through it. It brings you into great detail in terms of the chemistry that's going on, and it'll clarify. It's an animation. It shows you how the blast furnace works, so make sure you click that link as well. Now, what about the pig iron? So we've got all these big vats of pig iron. What do we do with it? Well, that depends on what people want. What have people ordered? Okay, because pig iron can be used to generate steel of various different qualities. And what we do with pig iron is we melt it down and we add in various different things. And the additives are what turn the pig iron into the steel that people order. So you can have different grades of steel for different reasons. Okay, building steel, and then you've got automobile steel and that kind of stuff. So different steels for different jobs. The way in which we form the different steels is by getting the pig iron, melting it down and adding things. So, as we said already, the pig iron is brittle and it's used for making manhole covers, car engine blocks and so on. Normally things that are very heavy, that's pig iron. Most iron is converted into steel. How? Well, first of all, oxygen is blown through the molten pig iron to remove any further impurities that might be there, like carbon and like sulfur. And then various different elements like chromium or manganese or even carbon are added to give that iron a steel that has been ordered, a steel that people want to work with. So pig iron, blow oxygen through, take out the impurities, and then add in things like chromium or manganese or carbon, and you will be able to generate steels of different grades and qualities depending on what people need to work with. All steel will contain iron and carbon. Now, carbon is there because it's a strengthening agent. Carbon strengthens iron, all right? And we dealt with carbon as well in relation to iron when we're dealing with stainless steel, back with the alloys. So it makes an alloy, and it also helps to slow down the corrosion of iron. And carbon is usually added to less than 1.7%. What are the environmental considerations? Is there any dangers to these things? Anything we've got to be careful with, for example, in relation to the atmospheric gases? or any of these products that are coming out, any of them harmful? Well, the first thing we've got to know is if you're taking ore from the earth, you're going to be digging it. And as you dig more and more earth away, you create potholes around the surface of the earth. So you've got the whole worry about what does quarrying do? Well, let's say, for example, there's a hill, and over time, we're going to excavate all of this here. So over time, what happens is that we end up getting all of this eroded away, and we get something like the following. We get a big crater like that left behind. But what they are telling us to do now by law is if we carry out the quarrying exercise to take out the ore we need to extract the metals, we must restore the landscape. So therefore you must put this back to its previous glory. And that means by filling it in with topsoil or putting anything that's there and rebuilding that again and allowing the flora and the fauna to use that same space they did before you quarried. Okay? Air pollution. We're coughing out carbon dioxide. We're coughing out carbon monoxide. We're coughing out maybe sulfur dioxides as well. So the air, the gases, I should say, that are produced before they are released have to be chemically scrubbed. And that simply means that anything that's harmful in those gases that are about to be emitted are removed chemically, so that the gases that we allow back into the atmosphere are harmless gases. Okay, the final thing that I want to look at is the electric arc process. So you take your iron from the ground, your iron oxide, you put it into the blast furnace, it undergoes a whole heap of chemical reactions, out comes pig iron. You then use the pig iron together with oxygen, blow it through the impurities, add in chromium or manganese, and then you sell it away. But the iron then that's out there and being used at times can be reclaimed, and iron can be recycled. Okay, so not all of our iron comes from the blast furnace. Some of the iron we have comes from reclaimed and recycled iron. And the way in which that happens is through what we call the electric arc process. Now, this is a very simple process. You take scrap iron, you throw it into a big vat, you zap it until it becomes molten, and that will purify it. You then take out the impurities and you purify the steel, and then you tap it off and it's ready, it's purified and ready to be sold on. So this is where we recycle. This is how we recycle iron that's out there, okay, or steel. It's the electric arc process. So what do I mean by the electric arc process? Well, it's carried out on scrap materials. There it is there. So you take all the scrap metal that you've been given, you put it into these huge big containers, and then you simply take 4 carbon electrodes and you heat them to massive temperatures, which will melt all of this stuff down here, and it will melt it into molten steel. Now at this stage, if there are any impurities in there, they'll rise to the top, they'll float. So the iron will fall to the bottom, the pure iron will fall to the bottom, the impurities will rise to the top, and we can tap them off by rocking this thing. See the tapping spout here? We can turn this on its side, we can pour off the impurities, throw them away, and then we can tap off the pure metal. So the electric arc process is a way of recycling. As we said, scrap iron and scrap steel. And again, there's a link down here. You can take a look at it, press it, see what the system does, see how noisy it is, and see how energy intensive it is as well. We charge up these little pots, well, not little, they're huge big pots. We charge them up with scrap metal up to about 150 tons. We then melt them. So large graphite electrodes will bring the temperature up way over the melting point of steel and melt it. Then we sample it. How pure is the steel at the bottom? Do I need to zap it again? Okay. We refine it. We blow through oxygen, and oxygen is wonderful for burning away impurities. Again, slag will be produced at this stage, which will float on the top. We tip it off. And lastly, then we tap off the iron itself back into pigs, and then we send it away for further treatment, where it's casted and treated in order to produce whatever it's going to be used for. Okay, so that's it. That's electrochemistry finished. That's the whole thing done. I know I've gone through that very, very quickly, but again, it's nothing more than the basic electrochemistry that we studied in chapter 1. My advice would be go through those slides very carefully, look at all the animations I've given you, look at the flash animations that are up in Google Classroom, and if you have any questions on any of those procedures, whether it's the electrolysis of molten lead bromide, or molten sodium chloride, or molten aluminium oxide, or molten, as we had it there, molten hematite or magnetite, Do let me know if you need any clarification. Send me a question and we'll try and sort it out for you.